Magnetism and magnetic fields is a tricky topic. You probably covered it for the first time back in year 7 or 8, or actually maybe even primary school. But how much do you actually really understand about how magnetism works at the moment? Probably very little. And to be honest, to get a really deep understanding, you're going to need to try and study this at university level. But what we can start to do now is to help build the foundations for that understanding. And we can start to look at some of the different kinds of applications for magnetism and understand it that way. We can also look at the equations, and then we can work as engineers to be able to represent magnets properly. Now, a lot of this was covered in GCSE, so I'm not going to go over that again. And what I suggest you do is you go back and watch the GCSE level videos again to make sure that that is all nice and secure in your understanding. What I'm going to do is I'm going to build on that with the A level, and there's plenty to cover there. A great place to start is by describing the magnetic field. With a permanent magnet, there's a field around it, which we represent using magnetic field lines, which I'm going to call flux lines here, magnetic flux lines. The magnet is strongest at the ends, which is where the flux lines are closest together. There is more flux in this area than this area. So we say that the magnetic flux density is high. That's obviously a really handy measurement to make, so we give magnetic flux density its own symbol, B, and use this definition to describe it. The magnetic flux density at a point in space is the force experienced per unit length by a long straight conductor carrying unit current and placed at right angles to the field at that point. Right, that's a lot of words, so let's unpack it. Force per unit length. So, B is proportional to F over L. Carrying unit current, so B is proportional to 1 over I. So the final equation is simply B equals F over IL, or rather F equals BIL. The other information in that definition is important though, so you must include it. We are considering B at a point in space. The wire is long and straight, so there are no end effects to worry about. And the field is perpendicular to the wire. Units are going to be newtons per amp per meter, but it's an important value, so it has its own unit, the Tesla. So the magnetic flux density is 1 Tesla when a wire carrying a current of 1 amp placed at right angles to the magnetic field experiences a force of 1 Newton per meter of its length. Notice how the definition of the quantity only used quantities in the definition, whereas the definition of the unit used other units. And that's all you need to know right now. Make sure you understand what magnetic flux density is and have a look at some of the field patterns for different configurations of magnets so that you're able to draw them accurately and correctly.